Hello, dear students. Again, Mr. Abdul with you. We continue our work with lesson 3.2, photoelectric emission of electrons. It is it's part number 4, as you see here. Okay, part number 4. In this part, we will cover the following objectives. Let me read them together. So initially, we will explain why the maximum photoelectric energy is independent of intensity, whereas the photoelectric current is proportional to intensity. Second, we to study the graph of maximum kinetic energy of photoelectrons against frequency or wavelength. Actually, here we would use the reciprocal of the wavelength. Okay, let me start together. Initially, we need to know what's the meaning of intensity and how does intensity affect photoelectric emission. Okay, intensity is proportional. We need to know that intensity is proportional. To study its effect, it's proportional to the power of light, where this power depends on two main factors: the rate of photons, which means how many photons arriving to the surface of metal during time. So here we are working with the number of photons, how many photons reaching the surface. And point number two, it's the energy of the photon, the energy of this used photon, which is proportional to the frequency and inversely proportional to the wavelength. Okay, so to study intensity, we are dealing with energy, and this energy or the total energy depends on two factors: the rate of photons and the energy of each photon. Here we have two main conditions. The first condition to understand intensity, we consider in it that the energy of the photon is less than the work function. Or we can say the frequency of the used light is less than the threshold frequency, or the wavelength of light is greater than the lambda maximum or lambda threshold. So in this condition, if the energy of the photon is less than the work function, the intensity doesn't affect photoelectric emission because already this photon is weak and it's not able to remove electron. Example that we remember: if the work function of this electron is 3 electron volt, this is the work function, and I'm using a photon with energy 1.5 electron volt. So when we increase the intensity, we are not changing the energy of the photon. We are changing the number of photons, right? So this intensity does not work here because you increase the number of photons, but this photon is weak, right? So the electron will not be emitted. So in this case, if we increase the intensity, no photoelectric emission. No electric emission. Again, I repeat, when we are increasing the intensity, we are not changing the light, same energy photon, just we are increasing the intensity. Just 1 minute, please. Let me move it up. You understand? So when we increase the intensity here, so here the energy of the photon is less than, again, the work function, means this photon is like useless, is weak photon. So when we increase the intensity, we are increasing the number of photons, the rate of photons, not the energy of the photon, So even if you increase the number of photons, but still these photons are weak, no photoelectric emission. You see? No photoelectric emission. So this intensity in this case is useless. Okay, is useless. I will show you a demonstration on this or a simulation on this, so you may understand me more. I will take example here, the red light. See, here, if you see, we have a battery. I fixed the volts on 3.6 volt, and I will use red light. Red light has high wavelengths, so it has low energy photon. And I try to the intensity initially at 0. I put the intensity at 16%. You see, light is directed toward the matter and no electron is emitted. Let we try to increase the intensity to see, do we have photoelectric emission? It's 50%, 52, no photoelectric emission. Increase more, no photoelectric emission. Increase more, 70%, 80%, 90%, 100%, and no photoelectric emission. In classical mechanics, they were thinking that if we increase intensity, we will get photoelectric emission. And this was one mistake of classical mechanics. As we see, the intensity does not work if the energy itself, if the photon itself, it has low energy, less than the work function. This is the first condition. Now we go back. Okay, so the first case, again, if the energy of the photon, if I see the energy of the photon is less, okay, the intensity doesn't affect photoelectric emission. Okay, we go to the second case. Now, if the energy of the photon is greater than or equal to the work function, or we can say by another word, if the frequency of light is greater than or equal to F threshold, or the wavelength is less than or equal lambda threshold. In this case, when we increase the intensity, again, here we need always to concentrate on the idea that we are not changing the light for the same light, because if I'm changing light, that will affect what? The energy of the photon, the second factor which affects intensity. Here we are fixing the color, just changing the intensity by changing the number of photons. Okay. Now, in this case, if I increase the intensity, it means I'm using the rate of photon increases. Yani the number of photons I'm using is increased. And we know each photon removes one electron. 2 photons, if I use 2 photons, 2 electrons are emitted. 3 photons, 3 electrons are emitted. 100 photons. So every time we increase the number of photons by increasing the intensity, so the number of emitted photoelectrons will increase. So therefore, the current in the circuit will increase. Let we see. So here, intensity is useful. Intensity is useful because this photon, the energy of the photon is greater than the work function. So we go back to our simulation to see a condition like this. So let we take a wavelength, low wavelength, like the one with sorry, this is the intensity, keep it low. Let we use the blue light, which has high energy, or purple light. Okay, as you see, and we increase the intensity a little bit. See the photoelectric emission. Here, as you see, we have photoelectric emission, even with low intensity, because this energy, or the energy of the photon, is greater than the work function. Okay. Now, let we try to increase the intensity. Means to use more photons per time. So let we see the effect on the circuit. Now the intensity is like 50%, 49%. See, more electrons are emitted. Why? Because more photons are coming to the surface. Okay, let me increase it more. It is now like 80%. See, let's give it a little bit time. So you see more electrons. Okay, more, I increase to 100%. So you see, like, more electrons you see will be emitted. You see, so as we increase the intensity, more photons are used. So by the way, more electrons are emitted. You see? Okay. So we get the meaning of intensity. So we realize from what we observed, like that the intensity of light, as we see here, depends on two main factors: that the rate of the arrived photons, which means like the number of electrons, uh, uh, reaches the surface per time, and the energy of the photon. So when we do not change the light, means the energy is the same. So every time we increase the intensity, we are increasing, this is the conclusion, the number of the used photons. Okay, so the result will be higher current in the circuit. This is the conclusion. Again, if the energy, all of these under the title of energy photon greater than or equal work function, otherwise intensity doesn't work. Okay. So the conclusion here, let me read the conclusion, because one little idea more here in the second part. So the conclusion that we read together, that means that the rate of 1 minute, the rate of emission of photoelectrons depends on the intensity of radiation. Of course, when the frequency is constant, we are not changing the frequency. So this show me that the rate of emission, this show me that the rate of emission, the rate of photoelectric emission, photoelectrons emission, we can say, is proportional to the intensity, is directly proportional to intensity. Okay, this is the summary of what's written here. Now we come here. We have a new condition where at constant intensity, it means if I is constant, if the intensity is constant, okay, and if the frequency of light is increasing, he's changing the frequency. That means something new happens. So if we need to increase the frequency, and we know that intensity is proportional to two factors, what are they? The rate of photons, okay, and the energy of the photon, two factors. So if he's increasing the frequency, and the result is constant, he said that the result is constant. So if he's increasing the energy, the frequency of the photon, that means the energy of the photon will increase as well, right? And the result is constant. That means in this case, we need to decrease the rate of photons. So the answer will be constant. So every time we have constant intensity and we are increasing the energy of the photon, that means, of course, that the rate of photons I'm using will decrease. This is the idea summarized here. Okay? Just to show you that intensity depends on not only on the rate of photons, even it depends on the energy of photons, the frequency, and its wavelength. Okay? Now we start doing some applications on intensity to fix this information more. That we read together. Here we have question number 6. Okay, light of a particular wavelength is incident on a metal surface. Okay, so we have light. So this is normal photoelectric emission. If electrons are emitted, so when he tells me that electrons are emitted, he is confirming that the energy of the photon is greater than or equal to the work function. It's very important when I read to understand what he's saying, right? So we have photoelectric emission. We need to, because if we don't have photoelectric emission, intensity will not work. So we have photoelectric emission. In this case, the intensity works. You understand? So, okay, what situation would result in more electrons per unit time. That means, what do we mean when we say more electrons per unit time? This thing is very, very important. How I understand that when we say more electrons are emitted means more photons are used, because they are directly proportional. Each photon comes, let one electron leaves, right? So more photons are used. So the rate of photons is more, right? So the rate of photons is more, means I'm increasing the intensity. What I'm doing, I'm increasing the intensity. So if we come to the choices, it will be either C or D. You see? So from the word more electrons are used per unit time, that means more photons are used, means the intensity is increased. Now we come to know what happens to the wavelength. He told me less kinetic energy per electron. So now we need to study what happens to kinetic energy. What is the formula of kinetic energy? Kinetic energy, to study it, always use Einstein's equation. E photon minus work function. Good. Did he change the method? No. So this is the same. It doesn't change. So the work function does not affect here the kinetic energy. So the only factor which affects kinetic energy is E photon. But I need to know what happens to the wavelength. Hc over lambda minus work function. So the wavelength here is inversely proportional to kinetic energy. So which means if the kinetic energy is decreasing, and this is constant of work function, which means what happens to the wavelength will increase, because it's inversely proportional to the kinetic energy. So the wavelength increase, so it's either this part or this part. So finally, the answer is D, as written in the answer key. You see? So these critical thinking questions related to our understanding. If you don't understand the meaning of intensity, it's not easy to solve them. Let me do another application on this. Another application. Okay. Question number 7. Okay. Here, let me read together. Blue light is shone on a metal surface. So he's using blue light. That means he's not changing the color. E photon is the same. It's shone on the, so here E photon is not changing the color. So E photon here is constant, is the same. And electrons are ejected. Perfect. So that means that the E photon is greater than or equal to the work function. We have photoelectric emission. So the intensity here works. We have photoelectric emission. Okay. At a given rate with a certain amount of energy. So, okay. If the intensity of blue light is increased, how I translate this? This is very important. When we increase the intensity, how I understand this? Means more photons are used. More photons are used. Maybe here some student ask me why you didn't say more energy photon is increased. I'll tell them that I didn't change the blue light. You see? So the only factor here affects the intensity is the number of photons. More photons are used means the rate of emitted electrons increases. So if we go back to the choices, it is choice number B. You see? So I get the answer, but I prefer to continue. Okay? Let we continue. Which describes the rate of the energy per, okay, and which describe the rate and the energy per electron. The only energy for electron we have is the kinetic energy. Again, to study kinetic energy, kinetic energy depends on a photon and work function. The photon, we didn't change blue light. We're using blue light, and we didn't change blue light, so it's the same. Didn't change. And the metal, he didn't tell me that he changed the metal, so it's the same. So what I understand from this, that the kinetic energy is not changing, it's constant. So it's either the first part or the second part, so therefore the answer will be part B. Okay? Okay, now my dear students, we start with a new idea in this part, which is studying the graph of kinetic energy, the maximum kinetic energy of emitted photoelectrons versus the frequency of photon or frequency of radiation or light. Is it clear? What's the aim of studying this? The aim is to know what's the meaning of the x-intercept, and the aim of understanding what's the meaning of y-intercept, okay, and the slope at the same time. To understand that, we need to do some derivation and comparison to reach the object we are looking for. All of us know to study kinetic energy and frequency of light, which formula relates them? Einstein's equation, which is, let me change the color. Okay, what's Einstein's equation? That kinetic energy maximum equal E photon minus the work function. Good. But I don't need E photon. I need the variable to be frequency and the function to be kinetic energy. So kinetic energy, we keep it. But instead of E photon, we can write HF minus work function. Now, if we compare this formula with the formula of straight line, which has y-axis y equal A, or we can write instead of A, it depends on the curriculum, we can write mx plus C or B. Doesn't make sense. So if we compare these two equations, we realize that the slope of the straight line equal to Planck's constant. So the first thing we conclude from this derivation, that the slope or the gradient of the line m is equal to Planck's constant. Should be equal to Planck's constant, which is very important. So we finished from the slope, from the meaning of the slope. Number two, if we compare c with minus phi, we realize that the y-intercept, mathematically, the y-intercept c is equal to minus work function. Okay, is equal to minus work function, which means if we need to calculate work function, it's equal to minus c. And we will solve later question on this. Okay, for example, if the value here is minus 2 and here minus 4 electron volt, of course, electron volt, that we can write that the work function, in this case, equal to minus into minus 4, so the answer will be positive 4 electron volt. Okay, this is one idea. What's remained? So now we know what's the meaning of y-intercept and we know what's the meaning of the slope. What's remained is x-intercept. Number 3, at x-intercept, we know that kinetic energy is 0. So if we go back to the formula, we can say that 0, which is the kinetic energy maximum, equal HF minus the work function. Is it okay? So instead of kinetic energy, what we write, instead of kinetic energy here, what we write, we can write 0. Then we can say that HF equal work function, or HF equal HF threshold. So H cross out H, so the frequency is equal to threshold frequency. So therefore, if we go back to the figure, we can say that the x-intercept here is what is represent the work function. You understand? So this is regarding studying the kinetic energy versus frequency. Even we have another types of graphs. If instead of writing frequency, they may write the reciprocal of the wavelength as you see in front of you. Look at this question. What do the values A and B represent? So same idea. I need to do the same derivation to study this graph. Instead, if he gave me instead of f1 over lambda, what I do? Follow me, please. Again, we start with kinetic energy. Einstein's equation, maximum is equal to E photon minus work function. Okay, so kinetic energy maximum, instead of E photon, I write HC over lambda. But let we keep lambda not down, it's like alone here, 1 over lambda. So when we say HC over lambda or HC times 1 over lambda, it's the same, minus the work function. So again, let me change the color. So again, this is the function, and the variable is not lambda, is 1 over lambda, because if I keep lambda, it will be inverse function, and we have a transformation. That case is not required from us. Okay, so now if we compare this with the equation of straight line, m slope mx plus c, okay, here we conclude that the slope here equal hc. So the slope doesn't always equal h. So the first thing we conclude is that m equal hc. So if I need to determine Planck's constant, it's equal to the slope, which is m, divided by c. This is very important. Number two, that c here didn't change. Still represent what? So still the y-intercept, c is equal to minus work function. So the work function is equal minus c. So nothing changes regarding here. Now, regarding x-intercept. So here, what I mean by b, so b here, sorry, by mistake, b here in the figure is c here, right? You understand me? So this b in the figure, the y-intercept in the figure, this b in the figure, it is c here, right? It's c here. So you can write here b, right? b equal minus work function. So therefore here we can write that b equal minus work function. Okay. Now regarding a, the value of a here, the x-intercept, we use again Einstein's equation, kinetic energy equal maximum equal hc 1 over lambda minus work function. We know at x-intercept y equal to 0, or kinetic energy is 0. So we realize that hc over lambda is equal, hc over lambda is equal to, so hc over lambda is equal, sorry, hc over lambda is equal to hc over lambda threshold. So implies that lambda equal to lambda threshold. Okay, so A will be equal to 1 over lambda threshold. Okay, I feel it's very easy and very clear now. Now let we do together, let we solve some questions together as application on these graphs. Here I see question number 8. Let we read the question together. Using the adjacent graph, answer the following question. I see here in front of me two graphs, two metals, metal A and metal B. He's asking me in part 1 which of the given metals has more threshold wavelength. To compare the wavelength of these metals, you don't have wavelength here in the figure, but you have a frequency. The student who know the meaning of this graph and the details of the graph, he should know directly that when he looks at this graph, he should know directly that the x-intercept here and here, they are threshold frequency. So here we have the threshold frequency of A and B. And we see very clearly that the threshold frequency of A is less than the threshold frequency of B. So to reach the threshold wavelength, you need to start with the given. So part 1, I start with the given. So using the graph, if we look at the graph, using the graph, so we conclude from the graph that the F threshold of A, metal A, very clear is less than the threshold frequency of metal A, of metal B. You see? And we know that the wavelength is inversely proportional to the frequency. All of us know this from the formula C or lambda equal C over F, okay, or V over F. So if the wavelength is inversely proportional, therefore the wavelength, the threshold wavelength of A will be greater than the threshold wavelength of B. You see? If I can't read the threshold frequency, I can't answer this part. Part number 2, which of the given metals has more work function? Here we follow the same idea, using always, because both of them depends on F threshold, using the graph or the information in the graph. So we can start the same way. F threshold of A is less than F threshold of B. Just 1 minute. So if the threshold frequency of A less than of B, and we know that the work function is equal HF threshold, means the work function is directly proportional to F threshold. Therefore, the work function behaves like F threshold. Therefore, we realize that the work function of metal A is less than the work function of metal B. Same like the previous part. Number 3. So this is, as you see in this graph, we don't have calculation, but they are checking our understanding. So from which metal the electrons will be emitted with more kinetic energy? As I told you before, always to study kinetic energy, we need to go back to Einstein's equation. What's Einstein's equation? Kinetic energy maximum equal E photon minus work function. Okay? If we are using the same light is used. We have same light is used. So the only factor which affect the kinetic energy is whom? Is the work function. So, and you see work function, you have negative, like inversely proportional with with kinetic energy. Every time we increase kinetic energy, we are subtracting more from E photon, so the kinetic energy will decrease. So the one with more work function has less kinetic energy, which means if kinetic energy, if the work function of A is less than the work function of B, as we proved before, we realize that the kinetic energy of A, of electrons from A, emitted from A, if I'm using the same light, is greater than the kinetic energy maximum for those emitted from B. Okay? I hope that everything is clear till now. So we continue solving with the new question. It's question number 9. Let me read the question together. The graph below illustrates the maximum kinetic energy of emitted electron versus frequency of the incident light of the photon. So as you see, this we are familiar with these types of graphs: kinetic energy versus frequency. Okay. Using the given graph, determine the frequency at which photoelectric emission will not occur. This is a question. It's like knowing question. We need to know that frequency. So here he's looking for what is the frequency at which will not occur. The photoelectric emission doesn't occur if the frequency is less than threshold frequency. This is knowing question. So when photoelectric emission doesn't occur if the frequency is less than threshold frequency. And the graph shows me that x-intercept present F threshold is 4. Is what? Is 4 times 10. Don't forget here to see the scale used. Okay, times 10 to the power 14. So here, if the frequency less than 4 times 10 to the power 14 hertz, no photoelectric emission. Is it clear? So it's that he's here. Here he's just checking if I know what's the meaning of x-intercept. Is it clear? That means, is it F threshold or lambda threshold, whatever. Part number 2 is asking me to calculate the work function. If I know the threshold frequency, it's very easy to know the work function because he didn't give me here y-intercept. So the only way to find the work function is to use the original formula of work function, HF threshold, which will be equal 6.63 times 10 exponent minus 34 times the frequency 4 times 10 to the power 14. After using calculator, we will get 2.65 times 10 exponent minus 4 joule. Okay, you see, till now this is direct question. It's not that hard. This is the last question. We will do it in this part. Question number 10 as application, more application on the graph of kinetic energy versus the reciprocal of the wavelength. So he's asking me to calculate the work function, to calculate the work functions. Actually, here we have 2 ways to find the work function, either to use the y-intercept or to use the x-intercept. But if we use y-intercept, it's shorter and faster. We remember that in this graph, we can derive it. Just to remind you, we said before that kinetic energy is equal to E photon minus work function. So kinetic energy maximum equal HC over lambda minus work function. If you remember, when we compare it with the equation of straight line mx plus b, we realize that the y-intercept equal to the work function. So therefore, the work function we are looking for equal to minus b, which is equal to minus into minus 2.47, so which will be equal 2.47 electron volt. Okay, this is first way. Maybe another student use the threshold, the reciprocal of the threshold frequency. And maybe another student says that 1 over lambda threshold equal Q times 10 exponent 6. Okay, then he get lambda threshold. Then from lambda threshold, he says that the work function equal HC over lambda threshold, and he should get the same answer. Okay, so there are two ways to find the work function: either to use the x-intercept, but you need to do more steps, or to use the y-intercept. Okay, then they asking me to find Planck's constant. Let we remember how to find Planck's constant here. The variable is 1 over lambda, so Planck's constant is, if we need to find it, hc equal to m, equal to the slope. So part number 2, by the previous comparison, we know that hc equal m, or slope, right? So to find h, Planck's constant, we need to find the slope first. We see together. So again, so to find h is equal to the slope divided by c. So the slope is, to find the slope. Okay, just 1 minute. So to find the slope, as you see here, the slope is y2 minus y1 over x2 minus x1. And y2 here is 0, while y1 is minus 2.47. So as written here. Okay, but this is an electron volt. You need to change it to what? To joule. So you multiply it by 10 by 1.6 times 10 exponent minus 19, right? Divide by x2 over x1, but this is multiplied by 10 to the power 6. Huh? So x2 here is 2, x1 was 0. So between brackets, here we put them between brackets. You need to change it. You multiply them by 10 to the power 6. So if you do this calculation on calculator, you get 6.59, okay, times 10 exponent minus 34 joule second, which close to the value we know, 6.63 times 10 exponent minus 34 joule second of Planck's constant. Okay, and that's all. Thank you very much. Thank you. Salam alaikum.